if you would like to download this presentation as well as a paper that I would like to share with you all, which is one of the most recent papers that I've written about actually quantum image processing. So please just go right here. Okay, either by using this tiny URL or by using this QR code. And I'll give you a few seconds for that. And if you cannot get this information now, it's going to be at the very end of the presentation and then in the last slide, okay? Well, let me start by thanking Kevin for inviting me here to talk here. It's a pleasure. I'm grateful for that. I would also like to thank my sponsors, because that's the way it is. So first of all, thanks to the university I work for, as well as the USRA, which is the basically the organization that has all the admin of the quantum computer, which is installed at NASA Ames Research Center, which is a computer that we had access to, that my group and I, of course, had access to from 2014 to 2018. And some of the papers that I will present tonight were basically written using this computer. So thanks a lot to them, because it was, well, you see, we didn't pay anything at all. It was a free access, and it was very generous from them to allow us to use this computer. Thanks to IBM, because some of the stuff that we're going to introduce to has been developed either on the on Qiskit, either on simulating or running a quantum algorithm, as well as using the HPC facilities that IBM has, and they gave us a grant for running massive simulations of quantum walks in their HPC center. Otherwise, it would have been impossible to get those results, because as you know, quantum systems in general and quantum algorithms in particular are very computing power expensive. So otherwise, it would have been pretty much difficult, but thanks to them. So now, now, to provide the grounds of this talk, I'd like to say that something that we may all know very well, but it's good to state it this way, that quantum computation is transitioning from being a very solid research field into several applications, into several other domains like artificial intelligence, machine learning, computational geometry, image processing, and many others. Yeah? Right now, it's basically a full ecosystem, which is still small, but with a huge potential to grow, because there are investors, I mean, global and regional, as well as very local investors interested in putting money into this field for many reasons. Global companies, entrepreneurs, governments, and here in entrepreneurs, I should add, because I just didn't have the time to update this slide as well as another slide. But in addition to these companies that you usually know very well, there is another company named Quantum South. Quantum South is a quantum computation company based in Uruguay, in Montevideo, in South America. And they've been very successful as well at developing quantum algorithms for solving optimization problems. As a matter of fact, in the Airbus challenge that was released in 2019 to 2020, to 2020, sorry, 2019 to 2020, the one of the finalists was Quantum South. So that's something that we'll keep in mind, because now the stuff is also growing in Latin America. And well, there are many companies like the ones you know very well, D-Wave, Google, Microsoft, etc., as well as startups. And as I said in here, just keep in mind that Quantum South is a big thing now. And as for patents, I mean, well, you all know that a good parameter in order to find out whether a market is growing or it's very well established. I mean, in order to decide how to enter that field, is to take a look at the number of patents that have been both filed and awarded over the years. So this graph shows very well that opportunities in the market, in the quantum technology market, are just there, open to be taken by anyone who's got the time and the talent. Having in 2020 just a bit more than 1,100 patents granted all over the world is a very good indicator of how exciting and open to new ideas this field is. These are, the usual suspects as for the countries that patent the most. The darker, the more patents. And these are, well, of course, the companies, some of the companies that file and get many patents on this. So it's just basically to give an overview, particularly for the members of the audience who were not that, knowledgeable about the current status, state of the art of this market. Now, in my group, what we do is that first of all, we founded the field of quantum computation in Mexico. It was a number of years ago in 2004. Then we work on a number of topics: quantum algorithms, quantum walks, quantum annealing, quantum image processing, which is a field I co-founded, quantum machine learning, which, as you know, is a very exciting and hot topic in our field. Classical, that is to say, digital simulation of quantum algorithms, because even though simulating quantum systems on classical computers, on digital computers, I should say, happens to be in general an MP problem, that is a problem for which we need to invest a lot of resources, time, computer power, etc. It is not necessarily the case for all systems. And also there are many advanced techniques for hardware manipulation and software production that would allow us to significantly reduce the amount of time and the amount of computer power that we need for certain simulations. But to do that, one needs to be, very focused, very, very well specialized on that. And this is something that we do in our group. And finally, on the development, we work on the development of novel methods for training quantum engineers, because, someone has to work here. Someone has to produce the products, the services that, based on quantum technology and quantum science, deliver goods to our society. So, and this is typically the place of an engineer in the production chain. Kevin, I wanted to ask you, would you want me to carry on just talking about the stuff, or would you like people to, it's perfectly fine by me to interrupt me in order to make questions. So I would like to leave it at that, if that is fine by you.
Yeah, I think you've covered a lot, and you can continue too afterwards. If anybody has questions, I was really, so you said 2004 for basically your founder of quantum computing in Mexico. Who else was around at that time in quantum?
In Mexico.
Or just, in global, but, global quantum presence?
Yeah, well, it was the US, of course, but it was mostly academic. In the US, it was the research groups held at, based at Caltech, Harvard, MIT. As a matter of fact, in 2003, I was at Caltech on a research stay, hosted by the Institute of Quantum Information, led by John Presley, so quite a nice, very powerful scientist. MIT was also working, from the very beginning in this field. Harvard, of course. I think at the Stanford also had some research, ongoing research on computing.
Yeah.
And on the other side of the Atlantic, it was in the UK, Oxford, Cambridge, and the Imperial College. In France, it was l'Université de Paris, as well as the INRIA, l'Institut National de la Recherche de l'Informatique et l'Automatique, in Grenoble, at the very pretty close to the border with Switzerland. And in Germany, there were a number of groups. I mean, quantum computing is very popular in Germany, in particular on the experimental side, as well as in Austria, with Anton Zeilinger and Rainer Blatt being the absolute leaders of the field there. I would say that there were also some research groups working in Japan and China, as well as in Australia, but they were to be, I think that they became way more famous just a few years later, after 2004.
Yeah, so you've definitely seen the ups and the downs with quantum. Does anybody else have a question for Salvador right now? You could go ahead to your next slide while people ask questions.
Okay. Thank you. Now, if you want to know what's going on in quantum information science and technology in Latin America, there are, a number of sources that you can get close to. One of them is this Facebook group that we have, that I administer and founded. And we got about 4,000 members now, pretty close to that number. And we basically talk about any topic in quantum computation and quantum information science, technology, legal issues, jobs, employment, which is a big thing. We had to make the field grow. And again, I'm sorry because I didn't include the slide that I should have, but let me write down what I want to say now. Last year, we had a very successful online event about quantum technology all over Latin America. And the name of the event is Quantum Latino. So if you look for it if you Google it, then you'll find it. You'll find the website of our event of last year, and we're going to have a second edition of it in June. So Quantum Latino 2022. Just to give you a hint of how big it was more than 1,000 attendees, 60 speakers, going from fundamental basic research to applications. We had a number of tutorials, and well, I mean, you see, I mean, English is the lingua franca for science and business, but working in our own languages, in French, in Spanish, in Portuguese, etc., it's also a very important thing, because many of our students are not necessarily very fluent in English, but still they got the talent, the capacity, the mathematical ability to enter the field. So that's why it's quite important to talk about these topics in other languages in addition to English, and that's one of the reasons that we had for founding and for carrying on with the Quantum Latino activities. Okay. Okay. So now let me erase this. And let me carry on. Well, now let us enter the technical side of quantum algorithms, because one of the first questions that we should pose in order to convince ourselves to work on the development of quantum algorithms, why should we do it? And the answer is that we need to find, I mean, the answer is to identify, to create new ways for solving very complex problems for which the solutions that we may have now are not satisfactory. Now, that usually means having problems for which the amount of time that we need to invest is just huge. In the scientific parlance of computer science, we may be talking about NP problems, NP complete problems, or NP hard problems. That basically means, in particular, NP hard problems are the technical jargon used to refer to optimization problems. So these problems have, I mean, they all have in common that it's terribly difficult to solve them, meaning to solve them in a reasonable amount of time, when the time comes for increasing the amount of data that we put as input in those algorithms, okay? So an example of this kind of algorithm, or this kind of problems that we need to find new ways to solve them, are the factorization problem, finding the prime factors of an integer number, and many other problems that you can think of now, like the one that was mentioned by Brian in the last episode, which was the traveling salesman's problem, and many others, okay? Now, developing quantum algorithms for solving those problems, usually, I mean, the benefit of developing quantum algorithms is to make things faster. But faster here means two things. Let me clear this. The first meaning of faster in this context is to take advantage of the power that quantum mechanics provides us with, just as a gift. This is basically computational speed up as a heritage of physical properties of quantum systems. For instance, if we are working with a serial computer, a very old computer, and all we can do is to execute one instruction at a time, then that's all we have. But if we are given a parallel computer that has several GPUs, that has a huge power that can be run in parallel, and we don't take advantage of it, come on, we are a truly bad programmer, okay? So if we are given powerful hardware, the least we can do is to take advantage of that, to make proper use of that hardware. That's basically what this slide is about. It's about using, for example, the quantum parallelism property of, which is just, I wouldn't say a trivial, but it's a direct consequence of the superposition principle and the properties of how to combine vector spaces for creating quantum algorithms. Sorry, Kevin, would you like to say something? Because I see you want to. Kevin?
No, you don't have to explain the math at all.
Okay. No,
I think a lot of us have seen it, but aren't doing it every day. So,
okay.
Appreciate it.
Now, that's one thing that we can do. But, and this is basically what quantum computation has been about over the last 30 years, to take to make proper use of the properties that hardware has. Another meaning of fast is to develop algorithmic strategies. Like, for instance, instead of running a brute force algorithm for solving the traveling salesman's problem, to use a way more advanced and sophisticated algorithm like the Bellman Bellman-Held-Karp algorithm. Now, the thing here is that the Bellman-Held-Karp algorithm has in its name, three of the most famous names in computer science. That is to say, developing this algorithm was terribly difficult, and that, well, the result of that was having an algorithm which is way less time-consuming than the brute force algorithm. Now, this notion of the development of algorithmic strategies in the quantum realm is something which is just an open field for research and development. There are almost no strategic algorithms, algorithmic strategies developed so far in the quantum realm. So this is a huge topic in which research efforts have to be put on. So to create a quantum algorithm, we need to have a complex problem. We need to have a proper understanding of quantum mechanics, and then to work very hard so that eventually we can get a good quantum algorithm. There are a number of tools that we can use, okay, both hardware and software. But now let me focus on the preliminary topic in order to introduce some of the research that we do in my group. There are many ways to develop quantum algorithms. One of them is this one, the quantum circuit, the quantum circuit-based algorithm, which is very popular. It's 95% of all algorithms developed in the quantum domain are produced pretty much this way. And one of the reasons, I would say that there are two reasons for developing algorithms using this method. The first one is that computer scientists like me find this structure very intuitive. It's very easy to understand the rationale behind the development of a quantum circuit because it's really close to the one we use for combinatorial algorithms or for combinatorial circuits. The other reason is that most of the papers have been written along these lines. But there's another way to write quantum algorithms, which is by using the Schrödinger equation. And the Schrödinger equation is very important, not only because it's the basis of quantum mechanics, but also because there is at least one very powerful quantum computer platform which runs based on this equation, which are the quantum annealers produced by D-Wave. Okay, so I'm saying this because the training of a computer scientist, of a quantum computer scientist, will necessarily, and quantum engineers will compulsorily include training in both ordinary and differential and partial differential equations, which is usually, I mean, this is seldom a topic in the curricula, in the syllabus of a computer scientist or a computer engineer. While for physicists, understanding the basis of computer science, theoretical computer science, that's going to be kind of an exchange for developing a proper curricula for quantum algorithms. Now, this is one of the techniques that are used to create quantum algorithms, quantum annealing. Basically, the idea here is to take the basis of simulated annealing, which is an algorithm created for basically escaping local minima by using probability distributions. And the point of quantum annealing is that in addition to that property of jumping out of local minima, by using a probability distribution, we use quantum tunneling. Okay? This is right here. So the combination of these two properties, one of them classical, the other one quantum, purely quantum, allow the scientific community to produce this method for basically solving optimization problems. That was the original meaning or intention of the paper written by Nishimori, it's over here, by Kadowaki and Noshimori. And then it was later on used both by theoretical computer scientists and physicists to develop algorithms. Now, if you're interested in this topic, and one of the reasons for talking about quantum annealing is that, as I said, quantum annealing is a technique created for solving optimization problems. And this is a very important thing to say in the context of the development of modern quantum algorithms. And this is because quantum algorithms developed in particular over the quantum annealing context solve combinatorial optimization problems, okay? And when we produce the mathematical representation of problems that are usually stated or found within the realm of machine learning, those mathematical models for machine learning are also optimization problems. See, so there is a huge link, and that's why the first important results in terms of developing quantum algorithms for solving several problems in machine learning, finance, and other fields came up with the quantum annealers. It was not only because they were first in the scene, but also because it's a platform that naturally solves these kind of problems. So if you're interested in learning more about this stuff, I strongly recommend to read two papers. This first one by Maria Schul and others that was published in Contemporary Physics in 2015. And this other one by Jacob Ayamonte and his group, published in Nature in 2017. Now, our research in this field, we produced a number of papers. I think that this one, I want to talk about this one first because it's an introduction to the field. In this paper, we explain in detail how we can program a quantum annealer in order to solve a number of optimization problems. So in this paper, you're going to find actually three examples, concrete examples of how to program this computer for solving difficult instances of optimization problems. Also, if you are interested in the field of computer vision, we published a paper, I can't recall when it was, 2018, in which we show how to formulate, the development of algorithms for quantum annealers is divided into several stages. And one of those intermediate stages is the representation of the problem using Cubo, which is a particular mathematical language. Okay? So in this paper, we show how to translate the stereo matching problem, which is a key problem in computer vision, into the Cubo language. And finally, we show how we could formulate the solution of very hard instances of the minimum multi-cut problem in trees using quantum annealers. So this is an example of an NP-hard problem that has huge applications, for instance, in the layout and maintenance and basically, on electrical networks, okay, and any other kind of networks that is massive, and both in terms of the number of nodes and the number of connections found there. Okay, so far, questions?
Any questions? Unmute. So that's the first time I heard combinatorial optimization. You said quantum algorithms and then an annealer. I guess how prevalent, as far as the applications go, how prevalent is annealing in general?
Say it again, I didn't understand, sir.
Yeah, as far as prevalence, how common are annealers in general?
Oh, they are, well, I would say that they are very popular. As far as I know, the quantum annealers are produced only by D-Wave. There is a very interesting technology platform using simulated annealing produced by Fujitsu, as far as I remember. But that, the annealer that they have is not quantum, it's classical. But still, it's based on the simulated annealing paradigm. But that machine is also very powerful. Although, as far as I know, it's kind of access to that is kind of restricted. So I will need to test the platform to see by myself how powerful it is. But as far as I've read and heard, it's a very good platform for solving optimization algorithms. Okay. So quantum annealers are, as far as I know, produced only by D-Wave, but they are very popular because access to those computers can be done by multiple ways. You can use NASA's computer. You can also use the computers that are installed in D-Wave's headquarters. Several companies also have quantum annealers by D-Wave installed in their own facilities. So yeah, that's what it is.
And does anybody else have any questions regarding applications with quantum annealing? Anybody here? I'll unmute you. If you think of anything, go ahead. You can go ahead, Salvador.
Okay, very well, thanks. Okay, now I'll talk about quantum image processing. And well, as you all surely know, digital image processing is a huge thing for many reasons. The first one is that we humans like to see stuff, okay? We are very visual. And it's also that by using digital technology, we can manipulate and extract information from visual data. So it's been a number of years since the development of the first techniques in computer vision, well, image processing, computer vision, pattern recognition on visual systems. And as a matter of fact, my first master's is in computer vision. And I decided to work in that field precisely because of how popular and powerful it is, right? And I would say that so far, many of the algorithms that we have so far in computer vision are sophisticated and fast enough to satisfy a huge number of needs in the market, okay? But still, there's a number of issues that have to be addressed, and I'm going to talk about them in the following slides. Now, quantum image processing is, first of all, an emerging field of quantum information science. I co-founded it. The first paper I published on this, it was in 2003. In the same year, a company in the United States also published a paper entitled Quantum Image Processing. So this is how it worked. This is how it was founded. And then since 2003, I would say that there's a fair enough number of research groups working on this, in particular in China. So if you go to the Dropbox folder that I talked about in the beginning, there you're going to find, in addition to these slides, a paper that I mentioned briefly in the next few slides. This is a paper that I wrote with my colleagues in China and Japan, in which we, our goal in that paper was to provide a healthy critique on the current state of the art and the next step ahead for the development of quantum image processing. One of the things that we have to do in this field is to realize in which fields or subfields of image processing we need to develop novel methods, and in which others we need to complement the development, the digital algorithms that are already being produced. For example, if working on visual pattern recognition, we need to solve an optimization problem, then that's pretty much the field of quantum algorithms. And then the complement, working in a hybrid method, we're having digital and quantum algorithms working together for solving this kind of problem is going to be quite important. There's another thing which is to be addressed, and it is the fact that the actual sensors that are used now for digital or for producing digital photographs, digital pictures, happen to be quantum in nature. So what happens now is that those sensors collect photons by using quantum mechanical processes, and then we turn them into classical data, into pixels, in order to later on run digital algorithms on them, and then to present information to humans or to computers. But the fact that we are doing no processing at all on the quantum information stored originally, at the very beginning of this process, within the digital cameras that we're using nowadays in our phones everywhere, it seems to me quite an interesting opportunity for the development of quantum algorithms for the specific direct and very profitable applications. Because the hardware is already there, it's using quantum mechanical effects. So what we have to do is to find out which processes would be advantageous to run using quantum algorithms, and then to produce the firmware that should be inserted into those systems. There could be, as I said, digital cameras, mobile phones, etc. So this is basically the lines along which we work on this paper, and this is what I'm going to talk about now. So the expectation in this field, in quantum image processing, is that we will eventually come up with advanced technology that will either outperform, enhance, or complement existing and upcoming digital technologies for image and video processing tasks. Now, the field has become quite popular for a number of reasons. First of all, as I said, that we like to see, we like to have visual stuff in front of us. And it's also because there are some interesting applications in medicine, military technology, and the entertainment industry. An example of the military technology that could be developed using quantum image processing as an input, as a component, is quantum radar. So that's one thing. Medicine also for producing a number of pictures in which we anyway use quantum mechanical methods to produce them, and many other examples. Now, a key feature of QIMP, quantum image processing, which is not to be found in other fields of quantum information science and computation, is the fact that image processing, no matter whether it is digital, quantum, analog, or whatever, image processing is a field which is right at the intersection of science, technology, and the market. You see, in 90-something% of the cases, the evaluation whether an image is good enough or not is going to be made by the human being. It's not going to be an evaluation based on quantitative methods. It is not necessarily the case that in QIMP or any other method for processing images, we're going to use the standard tools that are utilized in theoretical computer science for evaluating the performance of an algorithm. In here, you see, I mean, on the one hand, it's humans, the ultimate evaluators of how good the technology and how the outcomes are. And it's also that, by nature, the size of an image is not, well, you see, we cannot apply basically what I want to say is that we cannot use the tools of complexity theory, that is to say, to evaluate the performance of a quantum algorithm for image processing using the standard tools of going to infinity as for the input, the size of the input of an algorithm. And the reason is very simple. The size of an image is limited. The size of an image is not fixed, but it's never as huge as if, in order to make us need the standard tools of computational complexity theory. So the fact that this field is right at this intersection of science, engineering, and the market has proved to be quite difficult to understand for a number of people. And that was actually one of the reasons that we had for writing this healthy critique on the field, so that people can actually realize that the goal of quantum image processing is not to make breakthroughs, fundamental breakthroughs in quantum algorithm complexity theory, but rather to produce tools that can actually be useful for further image processing in different methods, in different instruments. Okay. Now, research in this field is carried out in several fields. For example, quantum image representation. That means the the different methods that have been produced for storing an image in a quantum system. Quantum image operations, for example, rotation, translation, and all the stuff, image segmentation, feature identification and detection, etc. Quantum image security, that's to say, security protocols, cryptography, steganography, etc. And finally, quantum image data retrieval. This part, I mean, all these fields are very important, but the field of data retrieval is really fundamental for advancing the field. And the reason is that if we perform, say, if we naively perform measurements on a quantum system that stores visual information, then the number of measurements that have to be performed in order to extract a significant amount of information from that sort of a 3D matrix in which we have stored an image is going to be excessive. So we need to use advanced techniques for, say, from the field of quantum tomography, quantum state tomography, in order to both accelerate and be more efficient at these data retrieval processes, meaning extracting information from a quantum system and to put it into what we would call now pixels. Yeah? And the reason for not having a lot of advance in here so far is the fact that in quantum image processing, I mean, the community of people working in quantum image processing is basically composed of computer scientists and computer engineers. So we need the input of more physicists who are way more knowledgeable about how to do quantum state estimation, quantum state tomography, in order to incorporate those techniques into the development of more sophisticated quantum algorithms for image processing. Well, what time is it? Say 30. I should hurry up. There's a number of methods that we have that have been produced for storing images in quantum systems. Qubit lattice is the method that I invented a number of years ago. It was my first paper, actually. It was, and it was presented in the United States in the at an SPIE conference in Orlando. And then since then, the community has been working on several methods for storing, processing, and retrieving images in a quantum system. This slide is from a paper that I wrote with a colleague at Oxford a number of years ago. And the reason for presenting this is that I want to show you how we could actually use quantum hardware for doing things that we cannot do now with digital hardware. and it is the following. If we take a picture, say right now of ourselves, and the pixels of this picture are stored in a digital system, then the correlations that would allow us to identify the here is my face, Kevin's face, everybody's faces, blah, blah, are going to be lost. So those correlations that we use for being efficient at identifying features in an image are lost when we store them in a digital system. It's not a fundamental feature or a property of a digital system. That's just the way it's been done since the very beginning of the digital era. But then if we used quantum entanglement to correlate pixels, and what we have in here is a very simple basic example of black and white pixels, okay? But if we use quantum correlations for correlating, if we use quantum entanglement for correlating pixels that actually correspond to an image, to a geometrical figure, to whatever it is, then that information can actually be stored in the very quantum hardware that we're using for processing the data, okay? And therefore can be later on used for retrieving the images that were originally stored in that quantum hardware, quantum memory. Of course, I mean, with current technology, it's going to be quite hard to do it. I understand that. But the goal of this paper was to show that in principle, we could use the properties of quantum systems and this very unique feature of quantum mechanics, which is quantum entanglement, for doing image processing tasks that are just or that are gone in the digital technology that we use. Okay, we humans do it all the time, but that capacity is gone in digital technology for the reasons that I just exposed. Okay, hold on. Oh. Well, this is something I already talked about, which is the fact that the sensors that we have in digital cameras, both CCD or CMOS, use a rectangular array of detectors to convert light into an electrical signal. And that's basically done by using a quantum mechanical phenomenon for which Albert Einstein was awarded the Nobel Prize in Physics, which is the photoelectric effect. So if we run some quantum algorithms prior to converting that quantum information into digital, into pixels, I think that's a huge opportunity there for advancing the field. For advancing the field. Well, okay, so that's pretty much what I would like to say about quantum image processing. These are just some examples of the stuff that we've been working in my group over the years. This is a paper that we wrote for running arbitrary rotations on a quantum image. And this is the paper I've been referring to several times. So we're implementing efficient image processing algorithms on quantum computers. As I said, you shall find it in the Dropbox folder that I shared with you at the beginning of this talk. And this is the book that we talk about, the book that I was privileged enough to write with my colleague, Fei Yang, a fantastic quantum researcher and a fantastic human being, I have to say. So I was really pleased to write this book, not only because it's a field in which I put my brain and heart for a number of years, but also because I was privileged enough, as I said, to write it with Fei Yang. Okay, so that's it for quantum image processing. I got about 5 more topics. No, I'm kidding. I got 2 more topics to talk about. But if you want to make questions now, I think it would be great to answer them.
Does anybody have questions for Salvador?
I've got one. My CCTV example, I think I made that up. I don't think that was in the book. Was that, I've forgotten how to speak English. That was the example that I came up with towards the end of the book, and the video and the practical application of it. So my example was, so I'm trying to fish for your feedback on whether it's a good example or not. So I'm a soldier, I'm somewhere dangerous, I'm shooting video back to headquarters somewhere, and the security, the quantum security of the image, I really don't want the bad guy to know where I am or what I'm doing. So if you were to intercept somehow, you would get just sheer noise. So is that a valid example? I think I made that up. I was trying to think of an example that I could give them.
Well,
that was
something
the the talk to the government of Canada National Research Council. Because the algorithm was in the book, but then I was trying to think what's a practical example of it. And that is something that the United States does these days for our elite of the elite, that we have these live video feeds coming out of some amazingly dangerous places. And imagine you could tap into that and you know live where they are and what they're doing. That's amazingly bad. So I would imagine that the benefit of quantum video would be you can't, it just scrambled. It's just noise on the screen if you were to intercept that. Is that correct?
Yes, it's correct. So, well, yeah, what I would say along those lines is that, first of all, if the information, either video or just a set of images, is stored in a quantum system, and it's stored, say, in an ingenious way, so that the measurement basis is not necessarily known or easily inferred by the enemy, then you basically have quite a high standard of security in that image or in that set of images or video, because the the opponent shall have no idea how to measure the system, and therefore most likely when trying to do that, it's going to just get scrambled stuff. It's going to get random data. And something else that we could do would be once the image or video has been turned into the classical domain, into pixels, we could use quantum image encryption methods. For example, some of them have been produced by my group and several others in Europe, China, etc. So that we use the enhanced properties of quantum encryption so to make it hard for the enemy to de-encrypt the data that you have there. So yeah, I think there's a number of applications. Something else which sounds really like science fiction, but who knows, maybe it's going to happen in a few years' time, would be to transmit video using entangled pairs. That would be just fantastic, you see, because by doing that, which would be something like a Wi-Fi quantum network, then the likelihood of being able to capture video or images and then making sense out of it would be just negligible, would be really, really, really small. So basically the quantum Wi-Fi would be very safe. And for military application, I think it would be just a great method not to be caught by the enemy.
Yeah, that would seem to be the number one. Well, you could think of other uses, but the number one application. And I think prior to that, my example was for static images, a map. I want to transmit a map to you, and same thing. I really, really don't want the bad guys to see what I'm transmitting to you. So that would be the application of quantum transmission or teleportation, even better.
Yeah, that's exactly what I was thinking of, teleportation.
Okay. Oh, thank you very much.
On the contrary, Ryan, thank you very much.
Any other questions for Salvador right now? Okay.
Shall I go ahead?
Yes.
Okay. So now let's talk about quantum walks, okay, which is one of my favorite topics. I work on that in my PhD, and that's really close to my heart. So hopefully you're gonna like, I'm gonna show you here because I try to make it, in addition to being instructive, funny. So the reason for working on quantum walks is that classical, what we would call in the field, classical random walks or just random walks, are a very useful computational resource. Well, I mean, it's a very useful resource in computer science and many other fields. For example, for modeling the behavior of the stock market, we can use random walks. Eugene Fama became very famous of that, and he actually won the Nobel Prize for economics precisely by working on a mathematical model based on random walks. And the basic model, the easiest model in my opinion to understand the behavior of a random walk is what we have here. So this guy, this gentleman is tossing a coin. Let me show you, hold on. This guy is tossing a coin. So if he gets heads, Froggy jumps to the left. And if he gets tails, then Froggy jumps to the right. And there are many questions that can be posed once we have tossed the coin, say, n times. One of the questions would be, well, what is the site, as for all the sites that actually Froggy could have jumped to, what is the most likely site to be found that Froggy can be found? The answer would be right in the middle, 0. Another question is how likely it is that we're going to find Froggy at the end on the tails of the distribution. And the answer is rather small, okay? And all the answers are basically provided by this equation, by the binomial distribution, okay? Now, what happens here is that random walks can be used in a number of a huge portfolio of applications, and in particular, let me raise this one. It can be used, well, as I said, Eugene Fama became, it's a funny thing because Fama is fame in Spanish. So he became famous being Eugene Fama, and it was because of the random walks, using them. And another, which is crucial to the development of quantum walks, an application of random walks in computer science is solving this problem, the K-set. The K-set problem is a fundamental MP problem. Well, it's a fundamental problem in computer science. It was the first problem to be proved to be MP complete. Well, the set version by Stephen Cook a number of years ago. Let me give an example of why it is difficult to solve this problem. Basically, what we have to do in the K-set problem is that we are given a number of binary variables, and these variables are combined in 2 different ways. The first one is that we put, say, for example, 3 of them. If we take 3 of them, either of them or their negations, we put them together using ORs, or operators, and then we put all these clauses together by using AND operators. And the goal of this problem is to find the values, to identify, to calculate, to do whatever we have to do, but to find the values of x1, x2, up to x6, so that when we substitute those values in this formula, we make P equal to 1. So assuming that you cannot see this, meaning the solution, the first question that could be posed is whether this proposition has a solution or not, okay? Which is not trivial to say, because, well, you see, I mean, it's hard to see a structure here. Another question would be, assuming that there is at least one solution to solve P, to satisfy P, is it easy to find or not? And the answer is that in general, it's terribly difficult to find a solution to a specific set of instances, a specific set of problems in this field. In general, if we have a proposition like this one P, but defined over n variables, n binary variables, the number of different bit strings that we would need to produce and to substitute in P is going to be equal to 2 to the n. Okay, that where n is the number of sorry, hold on. Where n is the number of variables that we have. So, oh Christ. Yeah, here it is. Sorry. So finding solutions to instances, to cases, to particular cases of the K-set problem is difficult in general. Okay, and the reasons that we have for being interested in this problem is not only theoretical. It's not only because it is important. This problem is important in theoretical computer science, but it's also because there's a huge number of applications of this problem, say in the manufacturing industry, in basically in any branch of the industry where we want to solve optimization problems. There is we can use this this problem. We can translate those problems into instances of the K-set problem, and it happens that one of the best solutions produced so far for solving the K-set problem uses a classical random walk. Okay. This paper was published a number of years ago, actually, in 1999 by Uwe Schöning, sorry. There's been a number of small improvements since the publication of this paper, but basically the idea remains the same. We use a classical random walk for modeling the number of errors that we have when producing bit strings and substituting those bit strings into P. So the thing is that since one of the best algorithms for solving the KSAT problem was produced or is based on a classical random walk, then there was a huge motivation in the quantum computing community for, on the one hand, developing a quantum mechanical version of random walks, and then on the other hand, to use them on a variety of different problems by writing quantum algorithms. So quantum walks are the quantum mechanical quantum part, sorry, the quantum mechanical count. Sorry, I've been speaking for quite long today. The quantum mechanical counterpart of classical random walks, and let me show you how these walks behave. Okay, so suppose that both Homer and this coin are quantum mechanical systems. Okay, so that's why it's quantum mechanical Homer. So Homer could be, for instance, a depolarization of a photon, okay? And this could be, well, not a polarization, it could be any other quantum system that's going to jump all over here. And this coin could actually be represented by the spin of an electron, okay? The point here is that what Bart is going to do, that he's going to manipulate a quantum laboratory in which he will basically he will apply a unitary operator to this quantum mechanical object, and will interact with his dad, with Homer, so that once Bart has tossed the coin once, Homer will actually happen to be, as we would say, in a quite relaxed way, an ambiguous way, but we would say, when translating this behavior into plain words, we would say that Homer happens to be in two different sites simultaneously. So once the coin has been tossed, Homer is going to be in these two sites, and if we measure Homer, then the probability of finding Homer on site -1 is going to be 0.5, which is also the probability of finding Homer in site number 1. And if we toss the coin again, then Homer will happen to be in 3 different positions simultaneously before measuring. And if we measure, then the probability of finding Homer in site number -2, 0, or 2 would be 0.25, 0.25 for the streams, and 0.5 for the one in the middle. And eventually, if we keep tossing the quantum mechanical coin and quantum mechanical Homer keeps on going over the line, we would produce probability distributions of this kind. Okay, that if we contrast the behavior of this, of these probability distributions with the one that we would expect to have for classical random walks, we see there is a huge difference not only on the shape of the probability distributions, but also on the fact that the probability distributions that are produced by quantum walks cannot be classified as Markov chains or Markov processes, because depending on the initial condition of the system, we shall have different shapes for the probability distributions. And that could be advantageous for the development of new quantum algorithms. Okay? A few examples, now I'm done with the math, okay? So a few examples of the research that we've done in my group in the field of quantum walks. There is this comprehensive review that we published in 2012. I'm working now on producing, the 10 years later version. Hopefully I'll finish this year. There's also this work that we published last year, in which we use both quantum walks and quantum tunneling for solving very hard KSAT instances. It's a paper which is freely available. We also use quantum walks together with very dear colleagues from Egypt, Ahmed and Bassem, as well as who's a Polish scientist, and Carol Fung from China. We work on how to use quantum walks for doing data encryption in a 5G Internet of Things scenario. And finally, there is this paper that we published in 2020, and this is a branch of our research that we've been nurturing since then. And it's basically focusing on the following problem. Suppose that you have a lot of biological data that corresponds to a particular species, and that data is about mutations. It's about the genotype of that species, meaning the genes of that species, and different mutations that several members of that species have been going through. The goal of this paper, the goal of this research branch that we've been working on since 2019 is to use quantum walks in order to identify in this kind of a massive networks, biological data networks, in which parts of these networks there will be mutations, for which there will also be changes in the actual body structure, or the in the physical structure of the members of the species that have been going through that mutation. Because the thing is that, you see, for many of the mutations that we go through in our lives, we just don't even notice it, because they have no impact whatsoever on the physical structure of our body. But some other mutations certainly have a severe effect. So the goal of this research is to find out by using quantum algorithms, and in particular quantum walks, when that happens and how. And finally, the very last topic I would like to address is just one more slide, which is this paper that we co-wrote with, well, this paper is the result of a research project led by Marcos Allende from the Inter-American Development Bank. And the goal of this paper, was Marcos invited Cambridge Quantum Computing. At that time, that was the name of the company. Now it's Cambridge Quantum, together with Honeywell, and myself, to work on the following problem. Blockchain, not only Bitcoin, but in general, blockchain in general, is basically it's a technology that heavily relies on cryptographic methods, on a number of them. Now, some of those cryptographic protocols happen to be vulnerable under quantum attacks for robust enough quantum computers that would be running Shor's algorithm. And the point here is that what can we do in order to provide additional resistance, additional robustness to existing and future blockchains? Because trouble, the trouble of having quantum attacks on blockchains is not only going to be important for the blockchains that are developed in 20 years' time. That's going to be relevant also to the blockchains that we have now. You've surely heard this saying, pick and attack later, pick now and attack later, which basically means get as much data as you can now, even if it is encrypted, so that you store it, and then when the time comes for having robust quantum computers that can run Shor's algorithm on, say, 200, 300 qubits, then you can use that computer and that algorithm for getting the data that was originally encrypted using any public key cryptographic protocol. So the goal of this paper was to show that it was possible to produce an additional layer, security layer, based on quantum technology to existing and future blockchains, so that when the time comes for these attacks, the blockchains that happen to go through those attacks shall not be severe, basically. That's what it is. Shall have an additional resistance layer. That's it for me. I would like just to say, as a conclusion, there are many things that I would like to say, but I would say that the most important is this one. This is the first computer that I programmed when I was a child. I was 9 years old when I am twisted my father to buy it. And then a number of years later, I was privileged enough to work on this early technology for quantum computers. So this is going to happen not only to all of us who are attending this talk, that I am very grateful for that, but also to younger generations, my students, our children, our grandchildren, who will be facing similar situations in the sense of being exposed to certain kind of technology in their childhood or their teens, and then as they grow up, they will be facing dramatically different technologies that they shall need to master, to command, in order to be proficient in their jobs. So that's it. Thank you very much.
Yeah, thank you. So you said this was number 4 for you today. This is your fourth talk today?
Yes, indeed.
Oh, yeah, thanks again.
Very pleased to be.
So do you have time for questions, Salvador?
Yes, of course.
The the first one is basically with partnerships. Could you elaborate a little bit more as far as your day-to-day work today? And it could be past, present, or future, organizations that you've dealt with and what you've learned from those experiences.
Oh yes, of course. Well, as you know, I mean, science is a global scenario in which the more people, the more talented people and organizations, the better. So I've been really privileged enough to work with many people and organizations from basically the whole world over these years. I think that partnerships with both academia and industry are fundamental for the development of this field, for making sure, as a matter of fact, that we don't get a quantum computer winter, which is sort of the threat that we have all over our heads. So what I do is well, in the past, I've had partnerships with British, American, Canadian groups. Right now, working with colleagues from China, the UK, the United States, Uruguay, Argentina, remember Egypt, of course. Ahmed, who's one of the greatest, one of the best colleagues I ever had. He's based in Egypt, Japan, and hopefully Australia in the near future. But yeah, I mean, the more the better. And I have to say that right now, it's not, I mean, honestly, it is not that hard to build those partnerships with the industry and academia, because digital communications make it happen all the time. I would say that the tricky part has to do with the actual goals that we have for each one of the partners that we would like to have. So for academia, it's the goal is usually advancing the field, producing papers or delivering talks, etc. The usual stuff in academia. For industry, say for example, when we were programming D-Wave's computer, now that we've been given access to this HPC platform by IBM, eventually to their big computers, it's sort of a mixture of interesting goals, scientific goals, together with maybe some money that we need to invest in this. But I would say that the key part of establishing a relationship or building a partnership with the quantum computing industry is to show that one has a very concrete case that would advance the field in a particular subject with potential concrete results. So this is something way more focused than the typical academia research program. But I would say that this is, I mean, it's reasonable to face this new scenario because the conditions on which each partner works are different.
Yeah, and I think we all captured that, Salvador. Here's some of the weekly headlines. You've been around for a while. You said 2004. This is your fourth talk today. You're in demand. So is this quantum revolution, have you faced this kind of buzz this year, and especially later last year after the IonQ Rigetti kind of stuff in October? Have you faced this kind of buzz over the course of your career for quantum?
Not that much. I mean, right now it's just madness. It's
awesome.
talking
Okay.
all the time.
Good to hear.
Yeah. Right now it's total madness, but it's a very nice madness, I have to say, because I can see how the field is just blooming. It's just growing. Right. I wouldn't like to say exponentially because this is a word that I don't like to use because it trivializes, the actual behavior, real behavior of a community. But I would say that it's really growing very, very fast. So keeping up, the pace is actually quite difficult.
That's good to hear. That's definitely good to hear. So Gabrielle, feel free. I'm trying to unmute all the mics here. And then if Russ, you're ready to, either Gabrielle or Russ, you can mic in. So they did post. So Gabrielle says, do you think we will see more independent work or startups based on quantum technology, ? It seems that a lot of companies are funded by the big companies are funded by the government.
I see. Well, my answer is that I do think that we will see more startups, as I would say in the near future and in particular in the mid future. And the reason for that is that is the fact that big companies are working on, well, on the one hand, on the development of quantum hardware, and also there are also big global companies that are interested, say for example Airbus, BMW, etc., that are interested in the development of quantum applications for solving the optimization problems basically that they face. Now the thing here is the fact that, I mean, whenever a global company is interested in solving a problem, what they usually do is that they don't carry out all the work. What they do is that they produce a value chain in which organizations are inserted. So startups have a great opportunity there, because by producing specialized components of the full solution, they can basically have, you know, quite good income guaranteed. So there's a motivation for startups to work on specialized subparts or components of the full solution of the problems that the big companies are willing to learn, are willing to solve in the mid future. So the answer is yes. I think we will be seeing startups and medium-sized companies in the arena eventually, but I would say much sooner than we would sort of think of.
Okay, thanks for answering. Thanks, Gabriel, for the question. So Russ asked, well, what level of QC power do you think is needed for practical use of quantum image processing?
That's a very good question. I think if we were to run quantum image algorithms on a quantum computer, we would need a huge number of qubits. So something unreachable right now. But I also think that if we use if we adapt the algorithms and the ideas that we have produced so far into existing devices, there is a good chance for advancing the field without actually having to wait to have a full long developed quantum computers for doing image processing. And as I said, one of the examples I can think of, there's something, an idea that I'm kind of obsessed with, is using quantum algorithms on the actual imaging hardware that we have now in digital cameras, both, you know, as a full object or inserted as a component in mobile phones or mobile technology.
Okay, so then Brian, you can ask him a question. You can turn your video on too. And then so Claudia, basically anybody else, just Philip, if you have a general question, you said you weren't sure about the technology, Kanaki, Matthias, or Ricardo after Brian.
Well, I'll start with the comment because it's faster, because anyone who may be unfamiliar with quantum walks, they're not just a possible way of solving problems, they're actually a way to encode problems. So where is Homer on that line? What's his position? What are the probabilities? That's actually a way of encoding a ton of information in a very small space. So when you hear Dr. Robert Sutor of IBM talking about a caffeine molecule, and you need 10 to the 48th, 1 times 10 to the 48th bits, and that's 1 to 10% the mass of planet Earth, but we can compact that into 160 qubits. The quantum walk is essentially a way of packing that information in there. So it's super cool, not just a problem solver, but the precursor to solve all sorts of other problems. But then the big question I have, since you've met Professor Preskill, and years ago I opened up a D-Wave account and I started looking into it, but then it was the first time I heard him say that there is no proven speed up to using D-Wave, and since then I've heard him say that multiple times, including fairly recently, there's no proven speed up for using quantum annealing. But so I characterize it as, yes, it solves problems, but there's no speed up in using it. But since you use D-Wave and you've met Professor Preskill, how do you reconcile D-Wave's optimization, problem solving, its speed up or lack thereof, or actually soon, I don't want to mispronounce her name, from Polaris QB. She uses Fujitsu. So I'd really like to hear that conversation, D-Wave Because she says Fujitsu is just as fast as D-Wave. So what is your take on, I'll use Professor Preskill's words, so it's not me, Professor Preskill's words, no proven speed up, but yes, obviously lots of people use it. Lots of big companies use it. So what's the 411 there?
I would reconcile the two views by using a single word. Yet, it's not fast enough yet. But who knows? Let me give an example of that. What I mean. Back in the Second World War, when the British were working on decoding the Enigma code, the Enigma system, the Polish were actually faster than the computers that the British had developed for doing that. So you surely know the story of this, the history of this, and the Polish scientists and mathematicians who first worked on the coding the Enigma code. They were really good at it, and they actually had computers, working primitive versions of computers for that purpose. So then they passed on the information to the British intelligence agency, and at Bletchley Park, it was Turing who was in charge of developing the early and then the more advanced versions of the bombs, the machines that eventually were used for decoding the Enigma code. Now, the point here is that in the beginning, the very first computers that were developed by both the Polish and the British were really slow, terribly slow, awfully slow, because those were the early versions of a technology that was to become more advanced. So and of course, by the end of the journey that Turing began with the bombs, those machines were fast enough to outperform any human being. Okay, and they eventually reached the solutions that they were looking for. I would say that we are pretty much in the same history here as for quantum technology. When it comes to having definite proof of computational speed up using quantum devices, there is not a single example right now, no matter what company we're talking about, no matter whether it is IBM, D-Wave, or IonQ, whatever it is. Why? Because we are in a very early stage of development. So I think, so that's one thing. When it comes to the practical use and the pragmatic arguments for or against any quantum technology, I would say that it is not time now to rigorously evaluate the performance of those systems simply because they are too young for that. We need to mature the technology to give it more time. And to do that, what we have to do is to create the virtuous circle that allow us to go from very small mainframes into the very fast computers that we have in our pockets. So we need to invest money, we need to invest human capital, talent, to focus on problems so that we will eventually find how to twist the engines, how to make things happen with existing hardware, as well as to propose how exactly we can actually modify the hardware that we have now in order to get computational speed up or any other advantage that we may find using quantum computers. So that's what I think. The theoretical models that try to prove or disprove the potential computational speed up of this or that quantum computational model, to be honest, I don't pay attention to them. And the reason for that is that I'm an engineer. And I know very well that I'm both an engineer and a scientist. So when I focus on the scientific side of my job, I tend to think in abstract terms, in mathematics. And by doing that, we necessarily leave behind many details that could actually happen to be crucial for the development of a technology. So when we engineers work on something, then we say, that part was missing, this part is missing too. And then we put the stuff together and then we make things happen in ways that were not foreseen, in the scientific advances that were produced before. So that's what I think. We just need to give time to this technology to mature. And in order to do that, in order to make sure that there are enough resources, that is financial and human resources for making this happen, we must work with the stuff that we have now. with the tools that we have now. Yeah.
Well
said.
Thank
Thank
you.
Yeah, thank you.
Thanks, Wayne.
So have you come across stuff like this, Salvador, Brian, anybody else, as far as the number of qubits needed to break Bitcoin?
Well, it depends on the cryptographic protocol that we are referring to. If we're focusing on the scenario that I mentioned a few minutes ago, I think it would be around a few hundreds of qubits. I'm not that. I mean, I don't know the exact number, but having say 500 qubits should be enough for breaking any standard. Sorry, any RSA standard that we have now, 500, 600.
Yeah.
When it comes to other cryptographic protocols or other encoding protocols, like, for example, hash functions, we don't even know whether it is possible to attack hash functions using quantum computers. Some people say yes, some people say no. My answer is, I don't know. We need more time to find that.
Sure.
There was this famous, this quite popular article a few days ago that was published by Science News, I think, or New Scientist, I can't recall, in which it was basically said that there was a need of having millions and millions of qubits for breaking Bitcoin. But they were referring to hash functions. No, they meant hash functions.
Yeah, the devil's in the details. The previous article, I actually found the article. I started to read it. Now I'm writing something for my newsletter on it too. Are you familiar with any? So does this make sense to you, Salvador? This is a Waterloo. Yeah. Yeah,
I mean, yes, I agree. You know, as you said, I mean, the devil is in the details. When this news come, you know, hype, with hype in one or another sense, you know, that quantum computers are going to break everything or quantum computers are going to be useless, I really tend to be really skeptical. So, well, you know, there was this famous article that was written about 10 years ago that was published at the IEEE Spectrum magazine, or the computer magazine. I can't recall. It was an IEEE magazine in which there was this colleague who basically said that he didn't believe in quantum computers and that it would be just useless technology. Yeah, yeah. Well, you know, 10 years later, we can see that that's not exactly right. It's just a matter of time and talent. Yeah, I try to get into primary literature as much as I can, usually just the abstract and the conclusion. But have you come across this type of research? You want to screen something, or what kind of research do you mean? You see the screen here? No, hold on. I'm sharing screen, so let me stop my share so you can screen yours. Okay, now here it goes. Okay. Okay, so this one. So this is, you know, it's a phys-org, vibrating atoms, but robust qubits, phys is fine. So I keep an eye on all this stuff. And like I said, like if, you know, I can get to the primary literature to read the abstract and conclusion, I can. So that's that one. And then, so there's all types of good news. So I'm leading up to the quantum Latino one. And then, so this one's the victory amol. So there's diversity, which is good in quantum. I think this specific one, so obviously the Quantum Insider, they have a lot of good articles that I find, obviously everything quantum, you know, so this is a video you can watch, you know, regarding his prize. And then, so you had touched on this a little bit, and could you just rehash the significance of this event? And you said it's going to be this year too, right? Yes, indeed. Well, the point of Quantum Latino is to gather people who are working on different sites and levels of abstraction in quantum information and quantum computing. The thing is that, you see, in Latin America, there is a critical mass of people who are either scientists or engineers, or who are working towards science or engineering degrees. So, well, basically what I want to say is that human talent is a big thing in Latin America. We really have a lot of talented people who work very hard in order to become world-class scientists or engineers. But the thing is that what we are usually missing in Latin America are big projects, are good concrete ideas towards which we can actually focus and work towards them, towards the solution or completion of them. That happens for a number of reasons. In particular, where one of the reasons is that Latin America is huge, it's really big. I mean, the region is really big. And then staying in touch and getting together and having and cooperating and working in projects is not that easy, because not only because of the physical distances, but also because of the political regimes that we have, the different economic development levels that we have, et cetera, et cetera. So the goal of Quantum Latino is to bring people together to talk about quantum stuff in Latin America and to find out and to identify, to create bridges among us, and of course with other communities like in the United States, Canada, Europe, Asia, in order to build projects. That's basically the goal of this. And those projects can be either scientific research based, or they can also be technology development based, or any kind of project, including educational, for instance. This is a big thing in the Quantum Latino community, to produce educational material for teaching quantum computing, not only in Spanish, which is the most widely spoken language in the region, but also Portuguese, because Brazil plays a key role. I don't know how familiar you are with this. I mean, you all with Brazil is a very, very important country all over the world, and in particular in Latin America, okay, for a number of reasons: their economy, their scientific and technological advancement. So information needs to be translated also into Portuguese, into French, and as a matter of fact, into English, because Belize, they speak English. Well, not to be translated from English to English, but what I mean is that there is this set of languages that we speak in the region, and the need to communicate among each other, among us, is very, it's very richful. You see, there's a lot of richness in all the activities that we are trying to make converge in Quantum Latino.
So yeah, what's the date for that, for this year?
It's going to be from the 9th to the 11th. Hold on, let me get the information here. Quantum Latino.
And we also have, it's World Quantum Day coming up. I saw that you supported it. Obviously, it was last year, the first year, I think. Anybody should take a check that out too. And if you have anything to say about that event too.
Sure, indeed, I will. Just the dates for Quantum Latino 2022 will be from the 8th to the 10th of June.
And then is it fully virtual this year?
Yes, it's going to be fully virtual. And well, so far it's going to be fully virtual.
Okay.
I think that's going to remain that way. And most likely in 2023, we shall have the event. Well, it's a mix, it's a hybrid event, virtual and in person. Now, the Quantum World Day is a worldwide event, a celebration day of all quantum stuff. Okay, the initiative comes from Portugal. It was founded by a very good friend of mine from my PhD times, and now it's a huge network. There's as a matter of fact, let me show you the Quantum World, because the Quantum World Day has a website. World.
I have it in the chat here. Yeah.
Okay. Okay. Well, now the Quantum World Day, the goal of this is to celebrate all over the world in more than 150 countries now, or somewhere around that number, to celebrate the existence of quantum mechanics, as well as the development, the applications that are being produced based on quantum mechanics. So it's basically a day to say, yeah, well, you know, this stuff is cool. And we should actually, I mean, not only scientists and engineers, but society in general could actually just have a look on it to see what can be actually, what can be good for society, what can be profitable, what could be beneficial in terms of the technology that is to be developed. And then the way it works is that each national organization, in Mexico's case, my research group and the people we're going to invite to celebrate this day, we'll have a number of activities, say talks, popular science talks, et cetera, et cetera. I mean, the activities really depend on the goals and capacities of each organization, but the goal, the ultimate goal is what they want to just I just said.
Awesome. Appreciate it again. Once again, let's thank Salvador for his presentation. I really liked how you did the writing on the slides. That's the first on the discussion, and that helps to captivate. So if you could send us whatever software you use, that would be awesome.
And then,
yeah, once again, he's PhD in University of Oxford in physics, postdoc at Harvard in 2008. And I think the postdoc was the quantum, right?
Oh, yes, indeed. Yeah. Quantum algorithms. Yes.
Yeah. So he's pedigreed into all this, and then co-founder in Mexico, for quantum, and then the imaging processing as well. And are there any last questions? You can unmute or show your video.
Hello, Salvador. It's Ricardo.
Hey, Ricardo. How are you doing?
Oh, pretty good. Awesome meeting. Thank you very much for inviting me. Also, all you guys, amazing. Kevin, thanks so much for these opportunities to bring science to all normal people like us. The question is, Salvador, our enterprise, our small company. For small companies, specifically in Latin America, in your opinion, the investment we have to do some research in quantums, how much is we going to be this investment? So, and also the topic, which topic we have to select. So, to get the money in Latin America is very difficult right now. So we have to be some specific. In your opinion, what is the first step?
Okay, thanks for the question, Ricardo. Well, I would say that the very first step to be taken in order to make a decision of investing money and human talent would be to be very careful about choosing the problem that we would like to solve. And then once we have that problem very well identified, then the next step is to characterize the solution that we would like to have. And then we do reverse engineering. Then we know the goal, and then we see how we can actually build a solution. Now, in your case, in the company that you lead, IoT is a big thing. Or is meant to be a big thing, as well as e-commerce. So I'm saying this because I know Ricardo very well. I work as a consultant for his company. So what I would do would be to say, well, if the company is really focusing on IoT, and then we need to provide an advantage to our clients with respect to the existing technology that our competitors have in Mexico, then, for example, I would try to put, as a component of existing technology that we have in the company, some quantum cryptography or quantum communication, but basic stuff, something that we can more or less straightforwardly implement in the existing technology that we have for our clients, that you have for the clients. And the reason for that is that once you see that small investment in hardware and adapting the technology and human talent becomes profitable, then you'll have a reason to look for more problems. Could be long-term problems or medium-term problems in which you shall be keen not only on investing money, but also in looking for money and the corresponding human talent for solving those problems. It becomes an internal thing, an internal motivation thing. That's what I think would be pretty much, the path to be followed by SMEs that are interested in using quantum technology, not in producing quantum technology, but in using quantum technology as a differential with respect to their competitors in the markets that they are competing in. That's what I think.
Thanks so much, Salvador.
You're most welcome. Thank you very much.
It's also worth noting when talking about limited funding that there are more and more systems coming online for free. Last I checked, you can still access D-Wave systems for free. IBM's been free for years. Xanadu just started offering one of its systems for free, kind of a limited one, but it's still something. QTech, so at least 4 off the top of my head that, you get, just a few qubits. D-Wave, it's been a while since I looked, but I think I had 2,000 qubits before they unveiled the 5,000. You could use that one for free. Unless you're using a ton of it, you get quite a bit of time with it also. So if you have limited funding, you can do quite a bit for free. And maybe, I've never applied for funding, but maybe that would help you get funding to be able to demonstrate something for free. And now we need more money to buy additional time, either with the 5,000 system or maybe IBM's Eagle or something like that.
Yeah, I fully agree. As a matter of fact, that's the way we get money for research in my group. For instance, the quantum walk-based algorithms that we produce, that we basically built for analyzing biological data, we produce the mathematical model, and then we also work out the simulation code, and we run it on every single free platform that we found. And when the time came for saying, well, we just can't do anything else apart from what we've already done in these platforms, then we applied for a grant to IBM to use their HPC platform. And that's exactly what I said. I said, well, on the one hand, there are no quantum computers that can run quantum walks directly. We would need to translate the mathematical model into circuit-based, for instance, and that was going to take a lot of time. So I said, well, now that you want to simulate quantum walks on a big platform, then go ahead, okay, because you already shown evidence of this being a good idea on small platforms, then go ahead for the big thing. So yeah, I fully agree with you. That's a good approach.
So and multiple times I've encountered people who have been paying through AWS, paying for D-Wave, and I said, you can just log into their website, right, and use it for free.
Yeah, I know.
If you can offer for something for free and earn money through AWS at the same time, okay, congratulations, that's a good one. I'm impressed.
Like for instance, for D-Wave, is it top of the line stuff?
No,
it
is not. It's not for IBM either. The quantum computers that you would have access, the IBM quantum computers, you would have access for free, a really small one. But the point again is to produce evidence of the research that we're carrying out. It's a good idea. So then you can apply for more and say, well, what I've done with this free stuff so far, so good. So now I need money to make it greater, to make it bigger, to make it larger.
Yeah, because chances are your project isn't there anyway to use big hardware.
Certainly not at the beginning. Yeah.
Okay. Any last questions? They could be very, very general. We haven't heard from a number of you. So anything about Salvador, his success in the profession, anything about grants or, research, his group. We didn't talk too much about his group, but yeah, any last questions?
Well, I want to throw in a verbal thank you. I've asked a couple of questions and I feel like I cheated that I've read a bunch of your stuff before we did this. So it's like, I'm following along, and
it's encouraged.
Especially the book, but some paper you showed on screen. Okay, that looks familiar with the triangles and using entanglement. I mentioned that in my talk also. So I'm like, okay, I'm taking less notes. I've seen that one before. So thank you very much.
Thank you, Brian. Thanks for attending and thanks for your comments.
We appreciate it. And then, if you have any questions or comments, feel free to reach out. Thank everybody for this episode 15. This is Southern California Quantum Computing discussion with Salvador E. Venegas-Andraca, the special guest. Thanks again for coming and have a good rest of your day. Take care. Bye.
Thank you very much. Have a great night.
Thank you.
Talk to you soon.